gravitational wave band. And I'm going to use this as an opportunity to kind of review pulsar timing arrays as well, the concept for people who are unfamiliar. So PTAs are expected to make a detection probably of the stochastic gravitational wave background within 5 to 10 years. And that's over a range of different kind of predictions of the level of the background and different modeling scenarios for the astrophysical populations. And the shape of the gravitational wave spectrum in the nanohertz band, as well as the overall signal level, encodes information about the different types of processes that are contributing to the evolution of supermassive black hole binaries. So if we can constrain the spectral shape of supermassive black hole binaries in the nanohertz band, we can say things about the kind of eccentricity of the binaries as they enter nanohertz frequencies, also circumbinary disk accretion, and other types of stellar scattering scenarios within the final parsec of supermassive black hole binary evolution. Loss, is that what I've written? Loss Schoon scattering, yeah. 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 Oh, sure, yeah. And if yeah, there is, and I'll go through that as we're going through it. If any questions at all about anything I'm talking about, no matter how basic, then let me know. I'll also talk about Gaussian process emulation of the kind of strain spectral shape that allows us to probe the environmental conditions of supermassive black hole binaries. And this is going to build on what John was talking about earlier. So the kind of strain spectral shape is something I'm going to focus on throughout the rest of this. I'm at my summary. Why am I at my summary? Okay. That's weird. Anyway, so I'm assuming that everybody is familiar with pulsars, what they are. They're rapidly rotating neutron stars which have a strong magnetic field, and their discovery is about 50 years old. In fact, the conference to celebrate the 50th anniversary is in September. They emit radio waves along their magnetic field axis. The magnetic field axis can be offset from the rotational axis, which means you get a kind of lighthouse effect. Whenever the radiation beam sweeps into the line of sight of our radio telescopes, we register a pulse of radiation, and that's why we call them pulsars. So here's an example of that pulse being registered every time it swings into the line of sight of our receivers. We actually don't use the canonical pulsars which were discovered first. We use a different type of pulsar called millisecond pulsars. They were discovered in 1982. They have very fast rotational frequencies. The theory is that they are associated with a companion star. They've accreted material from the companion that accretes angular momentum, spins up the neutron star, and it also seems to dampen the magnetic field. So you get the radio pulsars, which are spun up to very high rotational periods, and also dampened magnetic fields. So at one point, the rotational stability yes, because it's the electromagnetic radiation is being sourced from the rotational. Yeah, exactly. So it turns out that these are much more stable types of pulsars than the canonical early pulsars which were discovered. So the early pulsars, the ones that were discovered in 1967, are the ones that are up here. It turns out they're associated with lots of glitches. The shape of the pulse profile is actually not very stable, so we don't use them for precision timing, and we don't use them to search for gravitational waves. So we use these ones that are down here. Okay, briefly, this is a schematic of the process of pulsar timing. Whenever a neutron star swings its beam into our line of sight, we measure that with our radio telescopes. In North America, we've got the Green Bank telescope. We've also got Arecibo, which is in Puerto Rico. In Europe, we have a whole host of radio telescopes. There are ones at Jodrell Bank in Manchester in the UK. There are lots there's one in the Netherlands at Westerbork. There are lots of radio telescopes which are doing this. And in Australia, you've got the Parkes Radio Telescope, which is pretty famous. It was involved in communications with the Apollo missions back in the 60s and the 70s. And it was really the first to start in on precision pulsar timing for gravitational wave searches. So that's received. We then have to account for something called dispersion. Interstellar dispersion happens because the radio pulses are propagating through an ionized interstellar medium. So they're being subject to dispersion, which means that higher radio frequencies will actually propagate faster. Lower radio frequencies will be slowed down relative to the higher frequency components, and so it kind of gets smeared out in the arrival time. So different radio frequency components will arrive at different times at our telescope, and we have to account for that. We know how to account for that because radio frequency dispersion just scales as 1 over the frequency squared. So depending on the component that we're looking at, we just correct it all to a theoretical infinite frequency, and that means we can combine all of the different components together. We also do something called online folding. We have to fold the pulses because actually individual rotations and individual pulses of the pulsars, they look very messy, and we can't actually do anything with those. So what we do is over say a minute or a few minutes, we fold all of those pulses together, and that produces a sort of epoch-averaged pulse profile, which is very, very stable and reproducible. So over several minutes, we just fold all of these pulses together, and that makes something which is very stable, very reproducible. And that's what I mean by the fact that these pulsars are very, very stable. So they have a very, very stable, long-term pulse profile. No. So there are lots of theories about why the individual pulses they look kind of messy. It might be because although the rotation is stable, the actual emission mechanism might be somewhat stochastic. So as we might be intersecting different types of material as it swings into our line of sight, or the emission might be somewhat stochastic rather than a continuous flow of accelerated particles. It's something intrinsic of the pulsar, yeah. Okay, so once we do all of this sophisticated dedispersion, online folding, we get a mean pulse profile, and we reference a particular position of this pulse profile to a time, and then we can add that to the observation time, and that kind of gives an offset, or the arrival time of that pulse. And we can do this many, many times. We observe these pulsars over many years, and that builds up a vector of arrival times for these pulsars. We can then build up very sophisticated timing models of when we expect the pulses to arrive. That'll depend on the period of the pulsar. It'll depend on the deceleration of that. It'll depend on the time derivative of the pulsar, because they're actually going to slow down. It'll also depend on things like the sky location, the properties of the interstellar medium, and if the pulsar is in a binary system, so maybe it's accreting from a companion or some other type of companion star there, then it'll depend on the properties of the binary system. So all of these factors have to be taken into account to build up a very sophisticated model of when we expect these pulses to arrive. And it's incredibly accurate. We can time these pulses and predict when they should arrive to exceptional accuracy. And it's actually one of the big successes of modern precision astrophysics, is being able to time these pulses to incredible accuracy and make predictions that would seem anathema to other areas of astrophysics. So once we build up this model of when we expect the pulses to arrive, we then have to subtract off the true observations. So this is going to consider the timing residuals. So the timing residuals are what happens when we fit and subtract the model of when we expect the pulses to arrive from the true observations. So if we've got a very, very good model of when we expect the pulses to arrive, then this should be just sort of Gaussian white noise. And the error bars here, the fluctuation should be consistent with the uncertainties on each observation. But if we've made some error in the position of the pulsar, then you'll get some yearly periodic fluctuations. If you've made some error in the frequency derivative, then you're going to get a quadratic feature in your timing residuals. And if you have some proper motion of the pulsar and you don't fit that correctly, you're going to get this very expanding sine wave envelope. So the goal here is to get a very good timing solution initially, and then we're going to search within these small fluctuations for the presence of any gravitational waves. So the influence of gravitational waves on pulsars is from the following. The gravitational waves are interacting with the Earth pulsar system. As they go through the Earth pulsar system, they're changing the separation, the proper separation between the Earth and the pulsar, and that's going to make the pulses to advance or delay with respect to our best fit models. And so we're trying to search within those fluctuations, the timing residuals, for any influence of gravitational waves. So there are lots of collaborations that are attempting to do this. There's the European Pulsar Timing Array, which I talked about. They've got this one, this one, this one, this one, this one. Nanograv has the Green Bank in West Virginia and Arecibo. And the Parkes Pulsar Timing Array, which is the Australian collaboration, they've got the Parkes Observatory in Parkes, Australia. And we all kind of play together within the International Pulsar Timing Array. It's not a proper collaboration yet, so it's not as strong as the LVC. But at the moment, we're trying to strengthen the data sharing capabilities of the IPTA. No. There are lots of, timing pulsars is only one part of their job. They're doing all sorts of other radio astronomy as well. Okay, so searching for gravitational waves with pulsar timing. The sensitivity band of pulsar timing to gravitational waves is very much set by the observation length. So we're searching within a time series for a particular type of signal. So if you imagine doing a Fourier transform of a time series, then you can get components down to 1 over the total observation time, and you can get components up to the Nyquist sampling rate of that time series. So typically we're observing these pulsars over decades, 1 or 2 decades, for many, many times with observations taken every few weeks. And if you do the math, that gets you down to a few nanohertz and then up to a few hundred nanohertz. And the primary candidates for gravitational waves in this band are supermassive black hole binaries. So these are black hole binaries with components that have masses of 10 to the 8 or 10 to the 9 solar masses. Very, very different from what LIGO is looking at, very, very different from what LISA is looking at. Although there might be overlap in the astrophysics of LISA and pulsar timing arrays. So we'll be observing the very early adiabatic in-spiral of these supermassive black hole binaries. We're not going to see the chirp. We're not going to see the merger. So we're looking at something which is over the sort of decade or 2 decade stretch of time that we're observing it, pretty much looks like a sine wave. And we might get a handful or 10 cycles of the black hole binary. There are other types of sources in that. Did you have a question? Oh, you were just stretching. There are other types of sources in the nanohertz band that are on theoretically less sure footing than supermassive black hole binaries. These are decaying cosmic string networks. If you're unfamiliar with cosmic strings, then you're in the majority, because I'm not sure that many people know what cosmic strings are or can explain them well. But if you imagine ice and you get these cracks appearing as it melts, then you get a kind of cartoon picture of what cosmic strings are. They're topological defects in the universe, in space-time, as the universe goes through a phase transition. So these cosmic string networks are formed in the very early universe. And you get these infinite strings, cosmic strings, which are permeating the entire Hubble volume. And as they intersect with each other, they chop off sections of each other. They form small loops. And those loops decay primarily through the emission of gravitational waves. They can occur, they can emit all throughout the band of gravitational waves, so not only in nanohertz bands, but also could be in LISA, also could be in LIGO. It depends on the kind of cosmic string model that you have. Yep. Right. Right. So, yeah. So that only. I'll get onto it later. We have sensitivity roughly up to a few hundred nanohertz, but yeah, you can't say exactly what it's going to be because we have very irregular sampling, like you say. So typically, since we're looking at very red spectral processes, we don't try to observe up to Nyquist. We just include a few frequency components since most of the power is at low frequencies anyway. Oh, sure, yeah. So you can do an observation within a few minutes. So that's not a problem. Yeah. But we do have coverage over the entire day because you've got Australia, then you've got North America. You know, we combine all the observations. Yes, so this is a cartoon picture of what a cosmic string network looks like with the infinite strings throughout the Hubble volume in white, and then the small loops that have been chopped off in red. And this is the bicep 2 signal, which, you know, this is from their paper, which came out in 2014 or 2013. This is, you know, primordial gravitational waves should show up as a B mode signal, a curl mode signal in the polarization of the CMB. They haven't found this, but it should actually look like this. We should be sensitive directly to the primordial gravitational waves. We won't be trying to infer their presence through secondary things like the CMB. We'll actually be directly sensitive to the primordial gravitational waves. Okay. Now this is a pulsar timing array. This means that we time lots and lots of pulsars to try to extract the signal of gravitational waves. The reason why we do this will become clear in a second, but briefly it's because there are certain types of noise processes which are intrinsic to pulsars which will look a lot like gravitational wave signals. So there are intrinsic noise processes in pulsars which have very long timescale trends. So it's stochastic noise, and it looks very, very red, which means that there's power primarily on long timescales, sort of yearly to decadal timescales. And we're looking for a stochastic background of gravitational waves, so that will look like a red process with power primarily on decadal to yearly timescales. So we want to be able to separate the intrinsic noise from the actual gravitational wave signal. And what we do is we correlate the information across lots of pulsars, because the noise processes in each pulsar should be uncorrelated. So this pulsar can't know what the noise process in this other pulsar is going to look like. So if you correlate that information together, you're going to get 0. But the gravitational waves are affecting all of the pulsars that we're measuring. They're all sort of embedded in this bath of gravitational waves. So when we correlate that information together, we should get signal, and the noise should just go to 0. So what we're looking for when we correlate all this information together is a very distinctive signature, and this is the Hellions and Downs curve. This is the overlap reduction function for pulsar timing arrays. There are overlap reduction functions which are general to LIGO and to LISA. Basically, this is what happens when you cross-correlate the antenna patterns for pulsars in different parts of the sky. So this is telling us how much the arrival times in the pulses should be correlated between pulsars which are on this part of the sky, on this part of the sky, or in this part of the sky. Basically, as you separate the pulsars on the sky, the arrival times should be maximally correlated at low angular separations, should dip below 0, and then increase to 0.25. So this is a property of the quadrupolar nature of gravitational waves. No other process will induce arrival time correlations that look like this, as far as we know. And so this is kind of the smoking gun signature of nanohertz gravitational waves. If we ever claim evidence in the future for a pulsar timing array detection of gravitational waves, this is what we'll be reporting evidence for. The fact that we've got evidence or a Bayes factor for Hellions and Downs correlations between the pulsars. And to show you why you can't just do this with one pulsar or a few pulsars, let me show you. You know, if you have 4 pulsars, then you're only forging a few pairs in that set, and that's not really giving you a clear picture of that Hellions and Downs signature. But as you add more pulsars, you're filling in this angular separation space here, and that's giving you more and more evidence or a clearer picture of the Hellions and Downs correlation signature. Okay. At the moment, Nanograv is about to release a data set that has 45 pulsars. The International Pulsar Timing Aarray has 64 at the moment, has a preliminary data set with 64. That's because there's lots of overlap in the pulsars that are being monitored. So even though individual pulsar timing arrays have like 40 or 30 that are being monitored, there's lots of overlap. So in total, we have 64 distinct pulsars. So I referred to the fact that the primary signal that we're looking for pulsar timing arrays is a stochastic signal. So this is somewhat different from LIGO and LISA, which is trying to measure the actual waveforms or give evidence for individual systems. Pulsar timing arrays can do that, but lots of modeling schemes have indicated that the stochastic background from the entire ensemble population of supermassive black hole binaries is the one we should look for. It's going to pop out first. So a little bit of math. This is the characteristic strain spectrum of gravitational waves as a function of frequency as it's been built up from the entire population of binaries. So over here, you've got the strain squared of an individual binary, but because you're integrating over the entire universe and the entire population, you've got integral over redshift, integral over the mass of the primary in the system, and then over the mass ratio. So throughout the universe, you're going to have a distribution of the number of binaries in infinitesimal redshift, mass of the primary, the mass ratio, and then the typical time scale that they're merging over. You'll also have some dependence on the evolution rate. So this is how the black hole binaries evolve through frequency space as a function of time. And then this last part here is telling you how the gravitational wave power is being distributed over different frequencies when you've got an eccentric supermassive black hole binary system. So if you're unfamiliar with the idea, then eccentric systems don't just emit gravitational waves at twice the binary orbital frequency. They emit over harmonics. They can even emit at the fundamental frequency, which is the orbital frequency itself. Right, yeah. So spin for us is not so important. Yeah, Chris? Yes, it does. That appears, well, that's going to come in, I think, in this rate here. Yeah, you do have to, I mean, we're not too sensitive to it because there's lots of other slop in here that kind of absorbs that uncertainty. But we're just assuming the recent Planck cosmological values. And we're sensitive out to redshift 2, so that does give us sensitivity. But we're not sensitive to the black hole seed formation mechanism or anything like that. We're not getting back to huge redshifts, which give us sensitivity to, formation mechanisms like that. Okay, so now to sort of parse this equation, the different parts of the equation are telling us different physics. This part here is the co-moving merger rate of black hole binaries. That affects the overall signal level, and the kind of things that we can parameterize here are the M sigma relation, the typical dynamical friction time scale of black hole binaries, and I'll explain what that is next, and other things to do with the large scale structure of galaxies. It's between 10 to the 8 and 10 to the 10 solar masses. 10 to the 8, so like a few billion, roughly, solar masses. And yeah, we're dealing with probably equal mass ratio systems. We're not dealing with intermediate or extreme mass ratio systems. The second part here deals with the binary evolution. I'll explain more in a few minutes, but throughout the binary's evolution, it's not just dominated by the emission of gravitational waves. There are other types of environmental properties and environmental conditions within galactic centers which are driving the evolution of these supermassive black holes. So it's not always being caused by the in-spiral due to gravitational waves. And we can put that kind of physics into this part. And finally, as I said, eccentricity will factor into this part here, and it's going to affect the shape of this characteristic strain spectrum over frequencies. Okay, so whenever you see a pulsar timing array collaboration quote the upper limit on the characteristic strain spectrum, it's going to be at a particular reference frequency. So the best upper limit at the moment is a characteristic strain value of 1 times 10 to the minus 15. And that's always been referenced to a frequency of 1 over a year, roughly 32 nanohertz, which is a very dumb place to quote the reference frequency or to quote the upper limit, because we have no sensitivity to frequencies of 1 over a year. That's because we're subtracting out the Earth's orbital motion from all of these calculations, so any periods of a year or harmonics of a year are a very stupid place to quote that. Nevertheless, our upper limits come primarily from a few nanohertz, and then we use a scaling to bring that to 32 nanohertz. And the kind of physics that are affecting the characteristic strain spectrum at these different frequencies are going to be typically galaxy population uncertainties at large frequencies. So the merger timescale of supermassive black hole binaries, host relations like the M sigma, the fraction of galaxies which are paired together, redshift evolution of the population, all of this is affecting the overall signal level primarily at high frequencies. Then at lower frequencies, so lower frequencies correspond to larger orbital separations when the systems might still be coupled to the external galactic environment. So you have things like stellar hardening, interaction with circumbinary gaseous disks, and binary eccentricity. And I'll explain all of these in a few minutes. Things which might cause a diminished gravitational wave signal and affect the overall level might be stalling. So if the binaries get stuck at, say, a parsec separation, that means that the number of merging binaries or the number of binaries that are emitting gravitational waves in our sensitivity band is going to be smaller. Gravitational wave absorption, I'm not sure it's actually a problem, but there are some theoretical studies which have shown that gravitational waves might be absorbed at cosmological scales. Again, I don't know much about that, and I'm not sure how credible it is. Okay, so to reinforce that, at high frequencies, you've got a signal which can be indicative of the merger rate of massive galaxies and also black hole galaxy relationships. And then the shape at lower frequencies and the degree of this kind of turnover that you're seeing here can be indicative of the physics of the final parsec of supermassive black hole binary evolution. Okay, the upper limit refers to, as I said, the characteristic strain at 1 over a year, and we assume a particular power law model for that characteristic strain spectrum. So we assume that the characteristic strain also always scales at frequency to the minus 2/3. You're going to see that in a second, and that's only for upper limits. So we only assume that model for upper limits. So we can, when we do that, all of the information is coming from a few nanohertz, like I said. We then use that frequency to the minus 2/3 scaling to get the value at 1 over a year. The upper limit has been getting better and better as time has gone on, and we're actually cutting into interesting astrophysical territory at the moment. Oh, this? This is from probably, this is when Hellions and Downs in 1983 did this with only a few pulsars. They had limited sets of observations, limited accuracy. As time has gone on, more pulsars have been added to the arrays. The hardware has gotten better. The telescopes have gotten much better. And also up here, the primary improvement is from better methods. So this is the switch over to very sophisticated Bayesian methods that you're seeing here. Okay. Now, I said earlier that PTAs are expected to make a detection within 5 to 10 years. That'll depend on the kind of schemes that we have for observations. So the Parkes pulsar timing array produced an upper limit a few years ago, which was the best we have. So it's 1 times 10 to the minus 15. And that's really cutting into interesting astrophysical territory. But they could never make a detection with that because they only include 4 pulsars when they get their upper limit. With 4 pulsars, like I showed earlier, you only have a few pairings that are really not marking out the Hellions and Downs correlation signature. So if you just focus on the blue solid line in all of these, after 20 years, 4 pulsars gives you less than 10% detection probability. But if you have a large array of pulsars, in this case, it's the Nanograv 9-year data set, which had 37 pulsars, and then you then forecast that you're going to add a few pulsars per year and expand your array, then within 5 to 10 years, you're getting up to very high detection probabilities. That's true for the current state of the European Pulsar Timing Array, and then if you combine all of the data together into the IPTA, the International Pulsar Timing Array, and then this is the theorists' Pulsar Timing Array where everything is perfect and you don't have any measurement problems or receiver problems, and after 5 years, that really gets you high detection probabilities. So that would be something like the dream of the square kilometer array, the SKA, which will be operational sometime in the mid-2020s. Okay, the red and the blue here is where you have a signal level which is sort of like 8 times 10 to the minus 15. That's the prediction as it was a few years ago. The red is when you have a signal level of 4 times 10 to the minus 16. That's the prediction that's been revised with new sigma relations. So if you've got a shallower M sigma relation, then that means the mass of the black holes at higher sigma levels is actually smaller. Smaller black holes give you a weaker signal. So we don't know which one of those is correct, so we just kind of present 2 types of M sigma relations there. And the dashed is when you might have a turnover due to that kind of environmental interaction that I was talking about earlier. Okay, now I'm going to do a very quick run-through of supermassive black hole binary evolution and then tie that into how we can measure these types of effects. This is a merger tree of massive black holes. It's probably actually a merger tree of dark matter halos with the black indicating a black hole within each dark matter halo. And over cosmic time, these systems merge together to form larger halos, larger galaxies, and larger supermassive black holes at their center. So the prevailing theory of structure formation is that it's hierarchical and builds up from smaller systems merging over cosmic time. So if you take a particular example of one of these mergers, this is showing a galactic merger in process where you've got distinctive tidal signatures, and you can see these galaxies are interacting. So this is in the very early stages of the merging process. I guess this would be at the earliest stage of black hole seeds, say 20, redshift 20, and then the kind of systems that we're sensitive to are redshift 2 and closer. We're not sensitive to the initial seed formation mechanism or, say, the growth from redshift 20 down to redshift 2. We're only sensitive to relatively nearby systems. Okay, so within each of these galaxies is going to be a supermassive black hole at its center. So when the galaxies merge, the supermassive black holes will sink within that merger remnant, the combined galaxy, and they sink from dynamical friction. So dynamical friction is the combination of many long-range and weak scattering events with stars and with gas, and it's gradually causing the black holes to sink. And this becomes a very efficient way of getting the black holes together from large scales, so kiloparsec scales, down to roughly a parsec. But once you get to a parsec, you're still not in the pulsar timing array sensitivity band, and dynamical friction is no longer efficient at getting you any closer. So there's a problem, and that's the final parsec problem, which is famous within galaxy formation and supermassive black hole theory, that dynamical friction can't get you to where you need to be for black holes to merge on that large scale. So you may need additional environmental mechanisms at parsec separations and below to get you to a merging binary, to get you to a merging system, and to produce gravitational waves that we're sensitive to. So some examples of these are stellar hardening, circumbinary disk interaction, or simply binary eccentricity. So stellar hardening is when you've got stars which are essentially on radial trajectories within the galactic center, and they interact with supermassive black hole binary by scattering off it. So you get many, many scattering events happening. It's like a slingshot, and that star is ejected, and with it, it carries energy from the system. You're carrying away orbital energy from the supermassive black hole binary, and that drives it closer together. So the more energy you can extract from the system by lots of these scattering events, the faster you can bring the black hole binary to smaller separations. The same thing can happen if you've got a gaseous circumbinary disk, which is surrounding your binary system, that can extract energy from the system and drive it very quickly together. And finally, this is not necessarily an environment one, but if you've got some binary eccentricity, then that's going to make the system evolve faster to lower orbital separations. And the binary eccentricity can be amplified by a disk or with these slingshots. So what these interactions are going to do to the strain spectrum is cause a turnover at low frequencies. That's because energy is actually going into the environment rather than to gravitational waves. So at low frequencies, you have a reduction in the sort of signal level. So if you look at this characteristic strain spectrum, you've got sensitivity from one of the observation times. So this is 9 years. So that's roughly 3 or 4 nanohertz. And you just imagine you're observing the pulsars regularly up to a few hundred nanohertz. So that's a few weeks of observations, every few weeks. The dashed line is going to be when all of the black hole binary systems are simply evolving due to the emission of gravitational waves, nothing else interacting with them. The solid line is when you've got an interaction with lots and lots of stars which are scattering off the binary and extracting energy from the system. What this does is it causes a reduction in the signal level, and you can see this very distinctive turnover in the characteristic strain spectrum. So this slope here is it's actually after the minus 2/3, but you can't track that all the way back for a population that's undergoing many, many of these scattering events. Oh, yeah. Okay. And you can work out some very quick scaling relations for what the characteristic strain spectrum should look like at lower frequencies. So this is the calculation I was talking about that gives you the f to the minus 2/3. So we know what the frequency evolution is due to the emission of gravitational waves. We know what the strain scaling should look like, and you can actually do this very quickly on the back of an envelope. You get a characteristic strain spectrum, which is f to the minus 2/3. Mm-hmm. How do you get this? Oh, this? This is not the Fourier transform. This is not the Fourier transform of the... This is just the amplitude, which in the time domain is after the 2/3. Right. Yeah. Yes. Yeah. And the f to the minus 2/3 is coming in through this f dot behavior here. So if you just assume circular systems, you can get rid of all of this eccentricity stuff, and there's no frequency dependence in here. You know what the f dot should be after the 11/3. You know what the frequency scaling of the amplitude of the gravitational wave is here, and that gives you a characteristic strain spectrum, which is after the minus 2/3. And I think many people have worked this out over the year. One of the papers we quote a lot for that is Stirl Finney, a paper in 2001 that he never actually published, but he lays out all of the calculation in detail for this. That's if gravitational waves dominate the evolution. But if stellar hardening, these scattering events, if they dominate the evolution, then you have different orbital evolution of the binaries. When you work it out, that actually gives you an f dot of f to the 1/3, which means that at lower frequencies you've got a positive slope instead of a negative slope. And so at some point, you'll get a sort of handshake between where stellar hardening dominates and where gravitational waves dominate. That gives you the turnover. Right, well, the frequency is not, it's not evolving within our observational window, but yes, it's the frequency evolution of the binary. But we'll never, yes, it's when we take a Fourier transform of the time series of the data, this is the frequency we're probing. For circular systems, they're the same, but yeah, the binary will have made over many harmonics if it's eccentric. For disk accretion, you've got a different f dot, you've got a different scaling at low frequencies. This is just causing another turnover. And for binary eccentricity, we know that these two mechanisms, stellar scattering and disk interaction, can ramp up the binary's eccentricity, and that'll cause the emission to be distributed over many harmonics and can actually be pushed to higher frequencies, so you get a reduction in power at low frequencies. So again, you can get this turnover behavior. That's a repeat of the slides. Okay, and you can work out where this handshake or this behavior changes as a function of properties of the binary's environment. So we can just equate the frequency evolution under gravitational waves to the frequency evolution under stellar scattering, and just you're equating those f dots and you're working out where that changeover happens. So the bend frequency, where that turnover happens, is going to be at larger frequencies if you've got a larger density of stars in the galactic core, or if you've got even larger systems, that's going to occur at lower frequencies. So this makes the most sense, because if you think about a higher density of stars in the galactic core, this means that the binary is driving the environment is driving the binary for longer, and so it's still dominating the binary's evolution down to lower separations. The same occurs when you've got a larger accretion rate onto the primary black hole. If you've got a larger accretion rate, then the binary is being driven by the environment to lower and lower separations, and so that changeover in what's causing the binary's evolution will occur at higher frequencies. So we can work out these simple scaling relations which can inform where the environment is dominating and where gravitational waves are dominating. And what we've done within the last number of years is to actually probe the shape of the spectrum for information about these conditions. We followed a proof of concept study by Laura Sampson and Neil Cornish and Sean McWilliams, where they simply assumed that a combination of two things were happening. Either gravitational waves was dominating evolution, or some other mechanism like stars or gas. You can then rearrange the characteristic strain spectrum into a very simple formula. So you've got some power law at high frequencies. This is alpha to the minus, this is equal to minus 2/3 if you've got gravitational waves dominating the evolution. But then at lower frequencies, you can account for some sort of turnover caused by the environment. So what this is going to look like is what I've shown, which is a power law at high frequencies and then turns over at low. So we did that recently within the Nanograv 9-year data set analysis, and these are our sort of Bayesian spectral estimates. So this is a heat map of all of the spectra which are consistent with the posterior distribution in our analysis. Under a particular prior at high frequencies, we get different evidence for whether a turnover is favored at low frequencies. So within this analysis, we've locked the higher frequencies to a particular amplitude based on astrophysical predictions. This one came from Sean McWilliams and collaborators. So the level at this high frequency is fixed. We also had another astrophysical model from Alberto Susana and collaborators. Again, we fixed the higher frequency amplitude to this prediction, or to a range of predictions which are consistent with Alberto's or Sean's. We then allow the lower frequencies to float free according to this model and let the data constrain whether the lower frequencies follow a turnover model. So under this particularly optimistic amplitude level, we have to have a turnover at low frequencies and a very somewhat strong one. Otherwise, it would be in conflict with what the data is telling us. This is a more moderate prediction of the amplitude at higher frequencies, and so we don't need a turnover at low frequencies as much as we do in this one. So the Bayes factor was 22 in favor of a simple power law model. And then over here it was 2.2 in favor of a turnover model. Yeah, Chris? Yes. It's Bayes factor between a turnover model or a power law model. Yes, yes. No, we didn't do that because we're kind of locking it to a very high level here anyway at high frequencies. So it's not a fair example if we try to actually claim a detection. But this was just kind of investigating the low frequency spectral behavior. Any other questions about that? Oh, I'm sorry. Yeah, thanks for asking that. No, the 22 here was in favor of the turnover. And that sort of large value is coming from the fact that at high frequencies, we've locked the spectral amplitude to this very optimistic prediction of the signal level. So if you track the power law all the way back, it might actually be in conflict with the per frequency upper limits. Yeah, this is the Bayesian upper limits in terms of just individual frequency components that we're probing. You can see the lack of sensitivity at 1 over a year. There's also a lack of sensitivity at 1 over 6 months, but you can't really see that here. So if you track the power law back here, you're not in conflict with the upper limits as much. And that's why we need this kind of turnover. Yeah, but there's slop in the model, so we have to, this isn't much a validation of the priors and the astrophysical model predictions. No, these are real results. This is analysis of real data with priors on the signal level at high frequencies. You look dubious. No, you can see it's higher here. Nope. This is analysis without any modification of the data set. So why are we claiming Bayes factors when there's no? Yeah, it's between two possible signal models. So if there were gravitational waves there, then this would favor a turnover model with this particular choice of prior. So we're trying to probe any potential long timescale processes which are in the data set. And we're saying that although we're not claiming any evidence for gravitational waves because we don't have that kind of strong evidence, but if you simply look at the long timescale noise processes in the data set, and if you interpret those as gravitational waves, so let's say are gravitational waves, then what kind of spectral shape would those gravitational waves have to have? And they would have to have a turnover model, a turnover shape, if we locked the amplitude to different predictions at high frequencies. So that's all we're saying here. You know, there's no claiming of detection. We're just investigating what they would be consistent with if they were gravitational waves. Now this is formally correct as a model for two processes, gravitational waves and something else. But we want to expand the sophistication of this model and put in a combination of gravitational waves, stellar scattering, circumbinary disks, eccentricity, and also maybe probe things like the M-sigma relation. Then it gets very messy, might not actually be formally analytically tractable. You might have to employ some approximations in your calculations. But that's ideally what we want to do. We want to expand the physical sophistication of these models and not just be restricted to how clever we are by writing things down as a formula. So this gets us on to Bayesian model emulation using Gaussian processes. So this is different than what John was talking about. So John was talking about the idea of emulating waveforms for individual systems, but this is about emulating the statistical properties of populations. In this case, we're going to emulate the characteristic strain spectrum given by an entire population of black hole binary systems, which are being subject to different environmental conditions in the final parsec of galaxy evolution. So the idea is that we run a small number of potentially expensive supermassive black hole binary population simulations, and we can then train our Gaussian process to learn the shape of that spectrum as a function of the environmental parameters. So we can learn the spectral variance also due to the finiteness of the population, so there'll be some cosmic variance, or maybe even just some sort of Poisson noise due to the fact that maybe a few hundred binaries are dominating the entire signal level. We can learn that as well by running lots of different simulations at different environmental conditions. And that gives us a predictor for the shape of the spectrum and also that Poissonian variance from the Gaussian process emulation. And so a few of us wrote a paper earlier this year which built this Gaussian process emulation scheme for pulsar timing arrays. And we think it's the first time that Gaussian processes have been used to emulate statistical properties of populations, at least for gravitational wave studies. It's been done in CMB studies, galaxy power spectrum studies, but not for gravitational waves. We also hinted that it would be useful for LIGO and LISA studies, and I think the Birmingham group is working on this at the moment. Jim Barrett, Ilya Mandel, and collaborators have started doing this for LIGO populations. This was a conference proceeding. I assume they've got a paper in the works as well. So this is showing how we've built the Gaussian process model. Each of these individual red points shows where we performed some population synthesis simulations. So we've done this in terms of the density of stars in the galactic cores. So higher density means that there are more stars which are slingshotting off the binary and driving the binary faster. Higher eccentricity of the binary upon formation is also indicating that it's being driven faster through the band. So to get to higher eccentricities and higher density of stars, the characteristic strain spectrum at low frequencies is actually being reduced. So this is at a frequency of 1 nanohertz. So if you've got circular systems and no interaction with the environment, then you've just when you take out some of your simulation points. So on the left column here, we are showing the predictions in orange and the data as blue points with uncertainties. The band of orange is from many, many draws from the Gaussian process. So this is the band of predictions. And in this case, we've maximized over the kernel parameters. On the right, we have sampled over the kernel parameters. And there's very little difference whether you maximize or you simply sample as well. The x-axis is combinations of the eccentricity and the density of stars taken from the diagonal of the previous plot. So that's where the strain spectrum value was changing the fastest. So we're just taking the points along that diagonal as a way of testing the model fidelity. So with all the data, all of your predictions lie within the data points, obviously. But if you take out some points in between, so the red points are where we've taken out data in between, you're still pretty accurate. You're still getting that the predictions lie within consistency of the actual simulations. But then, if you take out some points at the end, so in this case you're trying to extrapolate rather than interpolate, your precision, or your accuracy is completely off. So we learned from this process that we should only try to interpolate rather than extrapolate. That may simply be because we're only using a particular kernel that's not totally appropriate for this problem. It was a squared exponential kernel with that was diagonal. So we didn't assume any correlations in the parameter space. Nevertheless, it's pretty good for interpolation. So now this is showing some mock data tests. So we've created a data set with a very strong gravitational wave signal in there, and we've injected 2 different types of populations into 2 data sets. So one is simply for circular gravitational wave, circular binaries with all of the evolution driven by the emission of gravitational waves. And then up here we've got a population of systems which are driven by eccentricity and the density of stars. In this case, the injection was not within the training data. So we're really trying to test how good our modeling scheme is. And these are showing posterior probability distributions. These are 68, 95%, and 99.7% credible regions for the posterior probability distribution. They're completely consistent with the injected values, and so we've achieved posterior constraints through this entirely experimentally conditioned model. At no point have we written down a formula for the strain spectrum. We've just allowed the gravitational wave, the binaries, to evolve under a combination of different physical processes, and then conditioned all of our modeling on the output of those population synthesis simulations. And this is what happens when we actually analyze the nanograv 9-year data set. I know this is saying mock data, but this is actually an analysis with a nanograv 9-year data set. This analysis, under two different types of priors, do you remember the optimistic prior and the more moderate prior? We can interpret the turnover that's being caused by these choices of different priors by different points in physical parameter space. So we're not just looking at the shape of the spectrum, we're also trying to interpret the shape of that spectrum in terms of the physical conditions that are causing that turnover. So for an optimistic prior, you're seeing that the data favors a large density of stars and also a large eccentricity of the binaries. But under more moderate priors, you're not favoring a turnover as much, and so that means you're not favoring as high eccentricities or as high stellar densities. So that's one technique that we've used to probe the shape of the spectrum and the astrophysics of supermassive black hole binaries. There was also a semi-analytic modeling scheme that came from the Birmingham group. So Shiwan Chen, Alberto Susana, Hannah Middleton, I think Walter was in there as well, and Alberto Vecchio. And that's semi-analytic in the sense that they did some fits to numerical experiments they did. So it wasn't entirely them writing down an analytic form for the strain spectrum. And they can probe things like the mass function of black hole binary systems. They can probe, I'm sure within their scheme, they can extend that to the typical time scale that it takes binaries to merge. And our modeling scheme can be expanded to arbitrary levels of physical complexity. So although we did a proof of principle in 2 dimensions, there's really no limit to how many dimensions you can increase this to. And finally, I think I'll end up with, these are very preliminary results for the nanograv 11-year data set analysis that's going to come out within the next few months. So you've got some optimistic predictions again for the McWilliams, Oestreicher, and Pretorius model. More moderate predictions that are coming from Joe Simon and Sarah Brooks-Ballore, and pessimistic modeling scenarios that are coming from Alberto Susana. And the difference in all of these different schemes is probably mostly due to their choice of the M-sigma relation. If you choose an M-sigma relation, I'm assuming everybody knows what the M-sigma relation is, but if you don't, it's a relationship between the mass of the black hole at the center of the galaxy and the velocity dispersion of the core stars, or the bulge stars. Higher velocity dispersion means you've got a heavier black hole in the center. Now, depending on which way you fit that relationship to the observations and which set of data you include, you could have a very shallow one, which means that you don't get very heavy black holes, or you can get a very steep one, which means you get very heavy black holes. Heavy black holes means a louder signal for us, and so that's the optimistic scheme, and shallower gives lighter black holes, and that gives us our pessimistic scheme. So this is showing the upper limits as a function of the individual frequencies. This is the typical scaling when we're dominated by white noise, so just noise in the receivers. And this is the sort of range of upper limits when we enforce a frequency to the -2/3 power law. And we're pretty much consistent with before in the 9-year data set. 2 years hasn't really bought us much. But what we did discover, and what the thickness of this black line is trying to indicate, is that we're sensitive to the particular model of the solar system ephemeris that we use. That means we're sensitive to the position of the center of the solar system in a way that we hadn't realized before. So if you get the mass of Jupiter wrong, then you can cause a big change in your upper limits and any detection statistics that you report. I'll talk about that, I think, next week. But basically, it's because we reference all of our observations to the solar system barycenter. So when we build our models for the arrival time of the pulses, there's a chain of corrections that we have to do. We measure the pulses, obviously, at the telescopes. We then correct that to the geocenter. That's then corrected to the barycenter. And then we have to trace the arrival time back to the actual pulsar itself. And so that geocenter to barycenter correction, it's called the Römer delay. And the position of the barycenter is very important in that calculation. That means we have to know the mass of Jupiter, trajectory of Jupiter, all of the planets, lots and lots of asteroids. And JPL does this every couple of years, but they actually can change quite a lot. The answers can change quite a lot depending on what data they've included and what fitting scheme they've used. So we're actually trying to incorporate new models which bridge the gap, kind of bridge the difference between all of those different JPL ephemeris releases. So we're kind of trying to introduce models which allow for some different tilt of the Earth's orientation or different masses of Jupiter, different masses of Saturn, all of these different things which could affect the position of the barycenter. So that's what's been occupying my time primarily in the last few months. I think it's kind of cool that we can be that sensitive to solar system dynamics. And we're doing this all in a very hierarchical fashion. So we're searching over all of the pulsar noise properties, all of the possible gravitational wave properties. We're also searching over the dynamics of the solar system, all of the different timing model parameters of the pulsars. So formally, this is a parameter space that's like 500, a couple of hundred dimensions at least. We can analytically marginalize over a lot of those, but we're still left with of order 100 parameters we have to sample. So I'll be interested to hear your talk. Is it tomorrow, efficient sampling in high dimensions? We think we've got the sampling pretty efficient at the moment. We're doing parallel tempering with a lot of different proposal schemes in there, but any type of optimizations would be good. Okay, I'll just finish off by leaving my summary there. We're expecting the detection within 5 to 10 years. Very little that we've seen can really damage that detection prospect. But any information that we're getting out of the shape of that strain spectrum and the overall signal level will tell us all sorts of information about supermassive black hole binary astrophysics, the way the binaries are driven to lower separations, and different schemes which can mitigate the final parsec problem, which is a big problem in galaxy evolution. If we can inform that, and if we can find out typical conditions, we'll actually be able to feed that back into the people who predict these signal levels. Gaussian process emulation was one scheme we used, and I think it's a pretty powerful method. It's very neat as well. I'm glad to see it has lots of applications, not only for individual systems, but also for populations of systems. So yeah, if anybody had any questions,